So if we see what we have now learned so far about the loop, and we compare that what we learned 2 weeks ago about the Hertzian dipole, and we say that both of these are now as dipoles in the z direction. That means that the Hertzian dipole is in the z direction, the typical case we had, and the loop is in the xy plane. So the normal direction to the area of the loop is in the z direction. And what we can see in these cases is that then we have many similarities between what we get out. So we have the same radiation pattern for these ones. So this donut shape. So the directivity is 1.5 times sine squared theta. We saw that we had an interchange between the polarizations. So the electric field for the dipole is here in the theta direction, while for the loop it is in the phi direction. So they are pointing in different directions, these two. And we will see that these actually have effects pretty soon. We can see a scaling of the dipole is KL. So that is the electrical length of the dipole. And when we go to the loop, it's in some way some electrical area of it. So it scales as K2 times the area. K is the wave number, so dimension 1 over meter. So K2A is dimensionless. And then we can see that the rests are the same. But in that, we have one more thing actually, and that is that for the dipole, there is a phase term. So in the dipole, we also have this J that sits there, that we do not have for the loop. And of course, this phase is in some ways arbitrary because we have huge phase terms in this distance that sits there. But the interesting thing is that they are shifted. And when we change the phase from 1 to J, that's a 90-degree phase shift, which of course will affect things, as we will see in these cases. The input impedance of the antennas, that changed from being capacitive here to become inductive. So the dipole is one piece of metal, you have one piece of metal above and one piece below, so that are two pieces of metal. It's a capacitor. While the loop is really that the current just goes around in a circle, that's an inductor. So it is inductive. So it goes from capacitive to inductive. And the radiation resistance then goes from a scaling of KL to a scaling of K2A2. So let's start changing this, and the changing what the relationships are with this, especially when we start shrinking things. So we really have this difference, as I mentioned before, that in the electric dipole, the scaling is as L over lambda, or this Ka, and in the loop, it's A over lambda too. And for small structures, this is then very important. That means that the area is much less than the length, because the length is small, and then you square a small number, that gets the area, and that is much smaller. And that is what we saw in the radiation resistance of the loop. It's much lower than the radiation resistance for a small dipole. And this will come in when we start looking at the helix antenna. We will actually see this in the helix antenna, these pieces. So that is one comparison. So that was a small loop. So now let's move to the large loop. And the large loop are these ones that are around one wavelength in circumference. So one wavelength now fits inside of our loop. That is what I call large in these cases. And we will do the same thing. We will assume a current in this wire. And we do the same thing as we did for, let's say, the dipole. So we say that this sinusoidal type current that sits there. So the current depends on the position of the angle, and in the same way as for the dipole, we had some cosine shape, and now we have a cosine shape in the phi direction in that case. And if we put this up, we can then write out what the current density is, and the current density is, again, it is in the xy plane. You have a certain radius that sits there. And then you can write up what is this phi component and this phi hat, points in some directions here in the X and in the Y direction. And of course we can ask, why do I do this? So if we start looking what this actually is in these cases, look at this animation down here. So this is now this large loop. And take a look at how the current is in some ways changing over this structure that comes out. And you can actually see that this is now very, very different for these cases. So here you get something that in some ways along these points here, which is where you should have fed it either there or there, the current is quite big and it's always pointing in the same direction, which means that it to the left, if it's pointing upwards, it points upwards to the right. If it points down to the left, it points down to the right. So they're always aligned, those two. And that is also the largest error I have here. So that is the part of the current that will be dominating the radiated field in some ways. If we look at other pieces of these ones, so we can go a little bit outside here, we can see what's happening here and here and here and here. There you can see that the current is much weaker, but also that they point in different directions. So they will kind of a little bit cancel each other, at least a little bit more, they will cancel each other. And especially this, if you were thinking that you look at the radiation out of this plane, then it is the same distance to all of them. And if they point in different direction, they do actually cancel each other. While these pieces that sits outside here, these two, they will always contribute equally and they will add up. So they will dominate the radiation. And if we see what this is that if I take these pieces I calculated of the current density here, and I now evaluate it for different points. So let's say that I take and evaluate it for this point, and probably this point and this point, and we can see what we get. So if I plug them in first in the these 2 points on the sides, so let's start with this one and this one, then this is what I get. So here I get a current that now always points in the same direction due to the added phase of this driven current that I have. Sometimes it's up, sometimes it's down. But you can see that both sides here. So let's say this is the minus side, this is the plus side, both points in the same direction. So they will contribute to this. And if I take the pieces that sits upside here and here, that is equal to 0. So the radiation here will really be dominated by 2 dipoles, which are separated some distance here. So you have some distance d between them. That will give the dominant contribution of the radiation pattern. And again, as we said in the beginning, if you compare it with your patch, then you had like this and this. There is a difference with the patch antenna because those were magnetic currents, but the pattern will be the same, but polarization will be different. So this should look pretty much the same. And we only have to determine what is the distance between them when this is happening. And then we have an idea actually what the radiation pattern is. So the radiation pattern is dominated by this dipole, and the distance between them is lambda over pi. So that is the separation. And the reason we know it's lambda over pi is that, of course, it's self-resonant here when the circumference is lambda. And then we can just compute what is the distance between them. So the distance from there to there, that is this distance d. And this one is lambda over pi. So that will give you an idea what the radiation pattern is. And that means that you will have a null in this direction, it's 0. In this direction, you will have some radiation, and it just depends on the distance that sits between them. And if you look in the direction out of the paper, you have maximum radiation, which is then pretty similar to what you had from the patch, but this also radiates downwards. So it radiates both out of the screen and into the screen. And if I would compare that with something, we can compare it with a folded dipole. So if we make a comparison between those two, you had the folded dipole down here, and we have the circular loop up there. And you can see that they are pretty similar. Both of them have a region here where it's inductive, radiation resistance is basically 0. Both of them have this anti-resonance here and there. And then they have their resonance frequency there, and they have the resonance frequency there. In these cases, I use slightly different scaling to make it more easy to see, because the dipole is, of course, in L over lambda, and the other one would be in the circumference over wavelengths, which was Ka. But it's pretty similar what we have in properties. And actually, the folded dipole down here, it is the same as a loop in these cases. It's just that the area of the loop is much, much smaller in this case. That is the only difference. And then the distance between the radiating dipoles, this d is of course much, much less than the d of these ones. Because in that one, these were on a circle that goes around here, which has a much larger separation between the dipoles. And that means that the folded dipole radiates more like one dipole pattern. But in the loop, we need to really separate them and see the phase difference between those two, and we get a different radiation pattern. So both are inductive for low frequencies, and the radiation pattern there will really be like a magnetic dipole. They are self-resonant, both of them, when lambda is the circumference. It's the same thing for the loop, which is this Ka1, and for the folded dipole, the circumference is 2L. So 2L is equal to lambda, that is lambda over 2. So the same property for the folded dipole as the loop. And the radiation pattern is then 2 separate dipoles for the loop and a dipole pattern for the folded dipole. That is the pattern that we get out from these cases. So that is in some ways an idea what's happening with this type of loop antennas. And the loop antennas, as I mentioned, is mainly used, I would say, as a receiving antenna if it's small. Larger loop antennas can be used in some cases, but they're really not seen as a loop anymore. They're really like a folded dipole or 2 dipoles that's a little bit separate. And there they are coming applications for them. But now what we will do is that we will use the knowledge of the loop to analyze 2 antennas which are very, very common, the helix antenna and the spiral antenna. Those are really good antennas for very different applications in some ways. So we will look into where we can use those 2. So let's start with the helix antenna. So the helix antenna is a typical thing that is drawn up here. So here you can see the helix antenna. And if you compare it with something, tape your piece of paper and look at what you have in the end of it here. And if that was made of metal, which it is in many cases, yeah, that's a typical helix. So you can just cut out a piece here and you have a helix antenna. You need to put it, or you almost always put it above a ground plane. It doesn't have to be a really large ground plane, but in most cases you put it above a ground plane and you feed it from below with a coaxial cable. That is a helix antenna. Extremely simple to build, an extremely good antenna. So that is our helix. And now we should, of course, understand how that is radiate. And if you just look at it first, could anybody guess how it radiates? I would say probably not, unless you have seen it before. But what you have learned from the dipole and the loop antenna would basically tell you everything you need to know about the helix. Not all the details, there are many like design rules that comes in, but the basic principles of the helix comes from what we actually have done. So when we look at this helix, we can see that there are many parameters. One is, for example, the diameter that sits there. So it's important to know what is the diameter. And of course, that sends your signal back to your loop in some ways. There is a height that comes in. What is the total height of this antenna? What is the spacing between the different turns? That's another parameter that sits there. If you have the diameter, you can get out the circumference of it. We saw it was important for the loop antenna. It will be important for the helix antenna. And then you can ask, how many of these terms have you done in your helix antenna? When it then operates, actually this can operate in 2 very different types of modes. One is an operation in what's called the normal mode, and that is the one that sits there. And this is the mode where it radiates like a dipole in some ways. So it's almost like a dipole. It has a dipole type pattern in some ways. And there is another mode of these ones, which is this one, which is then the more interesting one, which is the axial mode. Both have applications, actually quite big applications. The axial mode is more different from what we've done before, and the normal mode is very similar to what we had with the dipole, and I will show you very soon why. One thing that comes out with this is that they are usually elliptically polarized. So when we had the previous antennas, like the dipole and patch antenna, they have a linear polarization. The electric field is always pointing basically in the same direction. This will not be the case for these antennas, and particularly for this axial mode one. It has very different properties in how the polarization behaves, which makes this extremely important as an antenna. So let's start with the normal mode one, and we try to just understand what is happening with it. So we have a radiation pattern here that has its maximum radiation here, normal to the helix. So if you think it's a vertical, it's standing up vertically, it will radiate mainly in the horizontal plane. So like a dipole. And it can be quite small. So the diameter here should be smaller than lambda. And typically even the height here is much smaller than lambda. So it starts approaching this Hertzian dipole in some ways. And they can have either a dipole or a monopole pattern. And that depends really on the size of the ground plane. If the ground plane is very large, they radiate really like a monopole. If the ground plane is smaller, they start radiating more like a dipole. So they have this typical shape here of this sine square theta. So this donut type shape of its radiation pattern. And one of the big applications of this is stub helix antennas. So if we go back to prehistory, probably for you, so if you look at the older types of cellular phones, so really like almost a history talk, yeah, they typically look like this. Something was sticking out like that. I know that you have fancy cellular phones. I don't, but nothing is sticking out of this one. But of course, if I take these ones, the first one there, which was this blue one, it looks like this. You can see it on the screen. You can flip it open here. It was super cool when it came. You can even send SMS on it. That you could do nothing else. But up here is the antenna. And the antenna those days you could even take off. This is a stub helix antenna, which is a shortened dipole antenna. If you remember when we talk about the dipole antenna, we really start looking how can you make them smaller. And these helix antennas, stub helix antenna, are a really good way of making these much, much smaller. So inside of those ones sits something like this. Now I cannot pass those around so you can see them, and it's hard to see them on the screen. But that is what sits really inside of this. That is metal that is miniaturized in this way by in some ways folding it around. That's a typical case. There are a few different versions of them. So that is a big use of these ones. And of course, we need to understand a little bit how they radiate. Because what you can see here, if you take these phones, these were at the 500 megahertz band. And 500 megahertz is almost 1 gigahertz. So, you know, 1 gigahertz, 3 decimeters. Really big. You needed to make them smaller. And that is, of course, what you did with this. They are smaller. But if you should work really well, you did like this. And you had a full dipole that came out. That is the prehistory again that sits there. So we should understand a little bit of the radiation of these ones. So this normal mode helix. And if we start looking at it, we start thinking, how do I analyze this? I mean, this is a complicated antenna. So you could put it into FECO, you could simulate it in FECO, but let's make a simplification. So if you think about the helix that comes up here, so it goes like this, the helix, you know, it's rolling around up there. And then let's simplify that view and instead say, let's first go up and then let's go around, up, around, up, around, up, around, up, around, up. So instead of going continuously up as you do on the helix, you take one step up, you go round, up, round, round, and so on. Then you actually have a model of your helix as loops and dipoles. And we know perfectly well how to analyze small loops and small dipoles. Those are Hertzian magnetic dipoles and Hertzian electric dipoles. So we know that the loop here will contribute with something that looks like this, and the dipoles will contribute with something that looks like this. Both of them now have common terms. So in these cases here, we can see everything that sits to the right here are the same in them. So the radiation pattern in theta are actually exactly the same. The quantities that stands in front of it are different. And particularly this one and these ones are different. So one is pointing in the phi direction, one is pointing in the theta direction, but they're also 90 degrees out of phase. So one has this 1 and one has a J. That's it. So they point in different direction with different phase. And that is what will happen with this if not one dominates completely. If we take these antennas, the electric dipole part dominates so much, so it almost behaves like a regular type of dipole antenna. But if you get for a slightly different one, they can get more balanced. So then look at the radiated field. If I take first my Z-directed dipole, I will have my current in these cases, the electric field, just going in this direction, up and down here. So basically the same direction as the dipole. I will come back to your question very, very soon there. So if you see these ones, the current goes up and down like this. If we now add in these cases, so we add in now the loop, then I have to turn the electric field. So now my electric field goes like this instead, but it's phase shifted. So how do I add those two radiation patterns? Because I should sum the loop and the dipole, electric dipole. What happens when I add them up? Because the electric field here goes like this, the other one goes like this, and then one is multiplied by imaginary units. What would happen when I add them? What will the radiation look like in these cases? So let's take a look. It looks like this. And in this case, I took a very particular one here. I said now that these weights were equal. For a stub dipole, they will not be. But what you see here is a very different type of field that radiates. And this is something that's called circular polarization in these cases. And what's happening there is that your electric field starts turning around like this. So the electric field is not only like this or like this. It's rotating around like this when it's moving. And that is what's called circular polarization. And that's used quite a lot in different types of communication systems, for example. So here you have an electric field that then behaves or combines these two properties as we had, and a phase shift between. So that is a circular polarized antenna. And if you think your options for doing your patch antenna, you will do two of them. The second one option is to do circular polarized, which means you should do a wave that goes out and looks like this. It looks very fancy. It's a lot of fun with circular polarization. Okay, there was a question here from Khalad. The shape model in inductance here. I'm not sure I understand the question, so maybe you can elaborate.
I mean, the shape of the helix antenna.
Yes, so the inductance.
Is it here an inductance or?
So if we would look at that one, yeah, there are two different modes of it. And a very good thing is that I do believe we have helix antennas even for FECO, so you can run it. And you will see that for very low frequencies, these behaves like an electric dipole in that case. And then when it starts operating, you have different regimes where it starts operating. And there they work quite differently in some ways if you are in this normal mode or the axial mode of it. They will behave very different in that case. And I will show you some picture when we go to spirals where we actually look at the impedance for them too. So I will come back to that case when we go there. Okay, so that was this normal mode helix. And what we can see with these cases is that there is an elliptic polarization, and the quotient can then be asked what it is, and the quotient typically between the theta polarization and the phi polarization, which measures this amount of elliptical polarization, then scales with the separation here measured in wavelengths, compared to the circumference scaled in wavelengths. So depending on what the sizes are there, one or the other one will dominate in these cases. And a typical one for these ones, you know, old stub antennas, the dominant polarization is actually totally linear in these cases, because that term is so much larger in these cases, which means that this top of the part, the part in the top is much larger than in the bottom for these cases. So I need to say something about this elliptic polarization, because some of you might be aware about it, but some might not be. And the typical way of understanding these types of polarization is, of course, to get a feeling for what they are. And if we look at different types of fields and their polarization, we can in general say, let's take a certain direction, and then we can decompose here our electric field as something in the theta direction, so pointing south, and something pointing in the phi direction, pointing east. And then we ask, what are those components? If we plug that in and we look at the field, how it develops in time, we can see that we get a sum of two terms here. One which is the theta term and one is the phi term. And I have to look at those in some ways separately and see what's happening in these cases. If we do the antennas we have looked at so far, we have, for example, said this theta polarized one, which is the electric Z-directed dipole. It has only component in the theta. The loop or smaller loop had only the component in the phi that sits there. But when I start adding up these two components, so I add components that consist of both of them, I get contributions that goes, what to say, in both directions. So if we look at the electric dipole, here you have an electric field that just goes up and down like this. If I did my loop, it only goes like this instead. But then if I add them up with equal weights, so I look at this case here, then I'm there or I'm there. And here you can see that the electric field starts turning around like this. And it can either spin to the right or it can spin to the left. One of them is then called right circular polarized and the other one is called left circular polarized, because it can go in two different directions. And of course, I can have different weights on them here. So if I instead take a weight in these cases, that is 0.5, then it looks like this. So then it's following an ellipse instead of a circle. And of course, if I start shrinking the ellipse, so I make this distance here much smaller than what I had before, then it starts moving to the linear polarized. And that is what's happening, for example, in these stub ones. There is a small component of also this, what to say, the phi component that comes out from that one. But it's much smaller than the theta component. So it's approximately linearly polarized. But many antennas can actually have these parts. And in some application, you really would like to have it, because it has really good properties for some particular applications. So let's move on to some of those. So if I now would like to define what is this right and left in some ways, there are different definitions. And the antenna definition is that you actually look at your helix antenna. So you can look at how you have done with your helix that sits there. So this is a right hand sensed helix. So put your right hand side of it, the thumb points up, then you're really following basically with your fingers around it. But for the left one, you have to do it with your left hand. And the antenna definition of right and left circular polarized ones is that a right hand axial mode helix radiates a right circular polarized field. And the same thing with then the left one here. So this one down here, that one radiates a left circular polarized fields. That is the antenna definition. So it's really defined back to the geometry. And the reason for this is that it's easy to sit in this and say, okay, this go right and this go left, but then you can actually change a lot of things and it goes in the opposite directions. And what that means is that there are also other definitions. So if you ever would meet somebody and says you need a right circular, you need a left circular, you need to be extremely careful to check what definition they used. Typically in physics, they have a definition that is different from this. So there you also talk about right and left circular polarized light, for example. Light is an electromagnetic wave. And in many cases, it goes in the other direction. So we have to really look into what the definition is. So what is then our axial mode that does this circular polarization? It's now an antenna that should radiate outwards in the direction where it goes. And you create circular polarization with it. So you get out almost something that is perfectly circular polarized. It's a fairly directive antenna. So you can get the directivity here around 10 to 15 dB or dBi. You can see it in linear scale here. Very nice radiation pattern. Logarithmic scale down here looks slightly different because it depends on the range that you use to plot your dB scale. And this one, I think, is a 30 dB scale, probably that's it. These antennas are actually fairly broadband, not extremely broadband, but they have a good bandwidth. And what's happening in these cases is that the circumference here has to be approximately the wavelengths. So that means that this one is almost a loop antenna that sits there. So you can think about it as you remember when you had the loop that goes around, it radiated from there and from there. So two dipoles that sits slightly shifted. That is how the loop radiates. What does that mean from your helix? Then you can say I have one radiation there, and then you can move around to the other one, you have one there. And if you look in height, they are slightly separated. So one will be a little bit further up and the other one a little bit further down. So that means that they will have a phase shift. So it takes different time for the signal to reach them, and also they need to propagate a certain distance. So there comes in a phase shift. And in all of these cases, when you go around here, actually the direction of these will be changing. So it will always radiate in this phi direction, these currents, but with an added phase shift. And that is what creates this circular polarization that comes. So it's in some ways a loop where you had a slight phase shift between this one and this one in your radiation. And that adds this constructive part where it just rotates around and gets a circular polarization. We will also look slightly more about these ones a little bit later. And use of this is, for example, here. This is a GPS satellite. And if you look carefully around what sits down here, you can see a lot of helix antennas. There comes a lot of helix antennas in these ones. And then you can start asking a question. Why is this circular polarization often used in satellite communication and satellite systems? Because it is used in those cases quite a lot. So why do we want to put those up there? It's not that just I say they're pretty good antennas here. They are actually used in this. And there are a lot of reasons for that. And if you start thinking here, why can it be? So I have a small poll here for you. So one reason maybe is because you cannot align these type of antennas. So you think you have something up in space, you have something on Earth, and of course, if you're linear polarization, they should be directed in the same way. Another reason could be that you have a stable communication between them. So for example, if you send from a right circular polarized helix, you can receive it on a right circular one. And the crosstalk between them will be very small. If you had two dipoles, okay, this one and this one are orthogonal, but if you start tilting it here, you actually start receiving also on the other one. A third option might be that you have something called Faraday rotation in the ionosphere. And what Faraday rotation is that if you send in this wave, it starts rotating around like that. That is something that also happens in space in these cases. So let's do this and let's see what you believe in these cases. So what do you say in these cases? Why do you have this circular polarization in this satellites and satellite communication? Okay, Okay, we are in 50% of the votes. And we will stop in 2 seconds. So we end it there. So very equal results in these cases. Slightly more on the C case than on the A and B, but almost the same, 85, 85, and 100. So if I take this back here, all of these are correct, exactly as you say there. So if you think about the practical problem, of course, you can have a satellite up there, and you can say you can have this direction, and you should have this direction of the receiver, but it's actually pretty complicated to align stuff between space and Earth. So if you can avoid it, of course, you can avoid it. And if you add that the satellites would be slightly higher, and you actually have this Faraday rotation, it's actually impossible to align that. Because the Faraday rotation depends on this ionosphere, which is a layer far above Earth. And if the wave goes through them, how much this linear polarized is rotating when it goes around depends on the thickness of this layer. And those layers are constantly changing. So you don't really know how many they will go through. But if you have a circular polarization, you know, it's rotating like this, it goes through this Faraday rotation, it just rotates a few more laps. It doesn't matter, because the receiver will still see a right circular or a left circular wave that comes down. And of course, you can use this to transmit really orthogonal channels in some ways. So you can do right to right, and you can do left to left, and they are pretty good isolation between them. So it's a really good system to use in, for example, space communication. And circular polarization is used in a lot of cases there. There are other use of circular polarization, and you can have cases where you transmit a circular polarized wave and you have a linearly polarized receiver. It means that it's never perfect, but it's never really bad. Because then you can rotate your linear receiver here, and it doesn't matter in how you rotate it. You always receive the same. You lose a little bit power, but you never lose all of it. So circular polarization is actually a really good thing. And it's used in many, many cases. Okay, let's move to the next type of antenna, and that will be a spiral antenna in this case. So the spiral antenna is another version of these loops. And instead of taking the helix, you know, you put it like this and you move up, you do something like this. So you move out instead. So if you think down here, you have smaller loops, and out here, you can have almost like a big loop. So you take a wire and you just roll it and make it larger and larger circle that goes around. That is a spiral antenna. In particular, this is called an Archimedean spiral antenna. There is another one called equiangular, which we'll come back to later in the course when we talk about really broadband antennas. And if we take these ones, in this case, it has a diameter here of 75 millimeters, the one that we see. And if we look at the input impedance of these ones, so this is the S parameter, so the reflection coefficient, the magnitude of it. You can see here at very, very low frequencies, nothing happens. But when you go above approximately 1.34 gigahertz, the reflection coefficient is almost down to 0. So it comes a frequency where it starts working, and then it just works when you move up in frequency. Eventually it will stop. But you can see here that you have a bandwidth at least between, let's say 1.3 gigahertz and 6 gigahertz. That's pretty good. You will basically cover all mobile communication bands on the lower frequencies with one spiral antenna. Extremely good. Here we can see the input impedance of it, and you can see the same here. Reflection coefficient is fairly constant here, around 200 ohms in these cases, which can be used. You can match that. The reactance here is pretty much 0 for all high frequencies, and down here, of course, it's a mess. So there is a certain frequencies need to come into. And the interesting thing now is that you can ask, what is that frequency? When does this start working? Okay, what have we learned? We learned that you have a loop antenna. How big should the loop antenna be to work? It should be 1 wavelength in circumference. Then you can take this spiral antenna here. You can see outer part here is a loop. What is the circumference of that loop? And if we take that and we plug it in here, we can see that we had a diameter here, and we can then compare that with the radius of these ones. And if we just plug that in these cases, I can compute 2 pi a, so the circumference from that radius. That would say that that would correspond to a frequency that was 1.3 gigahertz, which is what you see here. So actually how this spiral works, or one way of seeing how it works, is really to take outside here that you have one big loop here. That is the first loop that you can make resonant. And that will then work at this frequency. The intuitive picture now is that when you move to a higher frequency, for example, 4 gigahertz, you find another loop here, which is a smaller loop. But that has a circumference around that wavelength, so 4 gigahertz. So that would have a circumference of 30 divided by 4 centimeters. And of course, you can find even smaller one here, which means you move even higher. So you can always fit a loop inside of this spiral that is resonant. And that gives them this incredible bandwidth. And you can, without problem, make an antenna from 1 to 20 gigahertz, a spiral antenna. If we look at some of the radiation patterns of it, here you can see first a very low one. So if we see at 0.5 gigahertz, that means you are below this resonance. And you can see this donut pattern that comes down. That's because this is an electric dipole. There's 2 separate pieces of metal. If you make it small, it will be an electric dipole. Whatever you do, you cannot avoid it. It will always come up. It doesn't work as an antenna, but if you were using it there, that is what it starts coming in. Outside here, you can see it start to be resonant. And it really radiates a nice beam up and a nice beam down in some ways. And is resonant for all of them. And that you can see when you just move around here, increasing the shape. And what we can see here is that, for example, the directivity goes up. So now it's up to around 3 in this case. If we look at it a little bit more in detail, we can see in the top one, that is the total directivity. And in this case, it's the directivity for the right circular polarized one. And in this one, it is for the left circular polarized one. And that actually comes from the direction where you are looking at it. So upwards, it would radiate a right circular polarized one. That is what you can see in the beam there. And downwards, it's actually a left polarized that is radiating in these cases. But very, very nice radiation pattern. Almost perfect antenna in that case. So another poll in these cases before we explain these ones. So we can see that these spiral antennas, they can have very large bandwidth. I didn't show you 1 to 20 gigahertz, but it's very simple to make this 1 to 20 gigahertz. They have very nice radiation patterns, very good for this, for many type of applications. The side lobes of these ones is really small, very low side lobes in these cases. And now you start asking, why don't you see them everywhere? If this spiral antenna now is so good, you have this bandwidth, you have nice radiation patterns. When do we find them? Why don't we find them everywhere? Or do we find them everywhere? And a really tricky thing now comes in, and that is related to, you have your spiral antenna, and you of course need to put it on something. So what happens here when they are attached to a structure? For example, you place them above a ground plane. You need to put them on a base station, you need to put them on an airplane or a car. So we'll make a new poll of these ones. And in A here, we have that the bandwidth become restricted to approximately lambda over 4 from the ground plane. Which of course would mean if you have 1 to 20 gigahertz, it's only at some of those frequencies you're close to lambda over 4 on the ground plane, which means you lose all your bandwidth. In the B case, you could create a nice broadband radiation patterns in only one direction. So you put it above your ground plane, and of course you don't radiate below the ground plane. And in C, it restricts the practical use to receiving antennas. So if you put it above something, suddenly you cannot transmit something. Or in C, it had to transform the radiated field from circular polarization to linear polarization. So those are the A, B, C cases of those points. So let's make one final question with this. And what do you think? And then we just explain what is happening in these cases afterwards. So what do you think there? A, bandwidth gets restricted to λ/4 distances. It gives a nice broadband radiation above the ground plane, restrict the practical use to receiving antennas, and it creates or transmits linear polarization instead of circular polarization. So 23% so far, a few more votes. Okay, I will close it down in 3 seconds. So we end the polling there. So here you can see the results. So the first one first and last one had the most votes, that you restricted to quarter of a wavelength above the ground plane, and that you do. So when you have this spiral antenna, and if it radiates down, the radiation will hit the ground plane. And of course, you need to add that radiation to what is radiated out again. And you only get constructive interference when the ground plane is at the right distance from your antenna. And if you were transmitting from 1 to 20 gigahertz, you had wavelengths between 30 centimeters and in this case is 1.5 centimeters. But you can only have the ground plane basically at quarter of a wavelength. So all your bandwidth will be lost, which means it's very hard to attach it to something. The B part also get quite a lot of votes, and unfortunately that doesn't happen. This does not behave as a patch antenna that you get nice radiation in one direction. You really get the narrow band antenna radiating in one direction. Not good at all. C is correct. So in the C case of this, I will have to stop this once so you can see them. In the C case of this, you have this actually that you restrict it to only receiving antennas. That's actually true. Almost all use of this spiral antenna is as a receiving antenna. It's incredibly hard to make a transmitting antenna out of it. And that is due to this, that you need to attach it to something. As an antenna floating in free space, it's a perfect antenna. But in reality, of course, why would you like to have an antenna floating in free space? You need to attach something to it because you want to receive or you want to transmit something. You don't just want to sit and have a good antenna. And to a spiral antenna, it's incredibly hard to attach anything. So then comes the question, why can I use it as a receiving antenna? Why does this work? Because it's true. C is correct. Do you have any suggestion how we could use it as a receiving antenna? Again, if we think the problem here is that if you have the spiral here, you know, like this, below it you put the ground plane. So I will draw this now instead like this. So here you have the spiral from the side, and here you have the ground plane. The problem is that this one radiates there and gets reflected up. And I need to have this because I need a hull or something to attach it. It's a big thing. I need to put it in something. So the question is, how can I remove this one? How can I take this away? And the trick to take this away is that actually you have your ground plane here, but you add another material here. So here I add a material which is called a radar absorbing material. So you put an incredibly lossy material under your antenna. What that will do is that will absorb 50% of the power. So that will absorb into heat. when you put that there. And that means you cannot transmit from it. Because if you were transmitting from this antenna, you would overheat your absorber. You will burn your absorber. But if you use it as a receiving antenna, the power levels are so low, so it doesn't matter if, you know, some is going to heat. It doesn't heat your airplane or something. And what it does is that you reduce the received power by 50% in this case. And this is an antenna that is used everywhere. So if you take these spiral antennas and you, for example, look at airplanes, especially like military airplanes, they're actually covered by this. They are sitting there as receiving antennas, basically listening to what's happening outside. Because you can put this antenna up there and something comes to it, okay, you lose the power in the absorber, but you get the signal. And if you just have, you know, you're flying with an airplane, you don't know what signals are coming to you. You want to notice all signals. So you need something that is incredibly broadband, which you have from this spiral antenna. But it's only receiving signals, it's not transmitting signals. And this is the perfect antenna for this. If you only want to receive, it's almost the best antenna you can build. Or it is, I would say, it is the best. At least versions of this. You do some modifications, not the really simple one I showed here. But it's an incredibly good receiving antenna. You pick up all the spectrum, fairly small footprint, but it only receives signals. You don't transmit on it. The D case that comes here, yeah, no, that's unfortunately wrong. It doesn't transform anything to linear polarization. What's happening with the spiral, as you said, it's sending up right there and left there. The left one hits the ground plane, and when it hits the ground plane, that transforms it to right circular polarized and goes up. So it still goes out a circular polarized wave, but it will be an interference between the one that is transmitted from your spiral and from the ground plane. So it doesn't really work, unfortunately, like that. So it's only like these cases, the A and the D in this case. No, the C, I mean, not the D. That is what's happening when you have these ones. So that is one of these spiral antennas, which actually is a really good one. I think I got a question there that you didn't understand the first point. Was that the ground plane? Khaled?
Yes.
Yeah, so what's happening there is that if you have your spiral here again, I will draw it again. We need to end soon. Okay, now I cannot draw. Now I can probably draw. So I have this one here and I have my ground plane here. What's happening here is that this one is sending out the signal that gets reflected up there. And the propagation distance to this one, now we say it's lambda over 4. Lambda is 360 degrees. So that means that this is now 90 degrees phase shift to go down. And that means that when you go up there, there is another 90 degrees. And if you add 90 degrees and 90 degrees, you have 180 degrees. So it's total out of phase. But what's happening is that when this wave hits the ground plane, in this precise reflection there, that is another 180 degrees. So you get 90 degrees from the propagation, lambda over 4. You get 180 degrees from the hit in the ground plane, and you get another 90 degrees with radiating out. And the reason or interpretation that you get another of these 180 degrees there, think about the image currents. You know, when you made the image currents over the ground plane, you have to shift the direction of the currents. And that shift is 180 degrees phase shift. So that is what's happening there. And another interpretation of this is if you do it with image currents, this one is again 90 degrees. And of course, this one is then 180 degrees plus 180 degrees. And then you have a 360 degrees phase shift and you're back where you started and you have constructive interference. That is what happens when you put it above the ground. Okay, I hope that answered your question. I've been running out of time, so yeah, we have one more slide to show. So I should also say you that the third quiz is opened. I think it's running at the moment. If you get any problems with it or something seems to be wrong, send me an email. Don't get angry at Canvas. Don't get angry at me either, of course. Instead, relax, send me an email. And make sure you get your first lab approved by the supervisors. You have one more week to do it. And next week, we will really start with array antennas. So now we've gone through some antenna elements. Now we'll see what happens when we put it into arrays. And if you think about communication systems, almost everything that's happening today is array antennas. And then we will have a new exercise also coming out next week. That's of course on Wednesday, it's a long time. And the next one is coming up on Canvas probably in this week. So with that,